Hi everyone, welcome to this webinar. In this webinar, I'm going to talk about the potential of AR technology to improve remote communication in maintenance. My name is Dedi Aryansha, and I'm a research fellow in AR for True Life Engineering for Cranfield University. Some points that I will cover in this talk are the research background and the problem of remote communication in maintenance. And then I will give an overview of how AR technology has been implemented to support remote maintenance. After that, I will talk about our work in developing AR-based remote communication framework to improve remote diagnosis. This will be followed by how we validated our approach by comparing AR versus no AR solution. Finally, some conclusion and further research in this area will be given in the last presentation. The ultimate goal of maintenance manager in any industrial sectors like aviation, manufacturing, and railway is to maximize the uptime of their production asset and to keep the downtime minimum. Every physical asset is subject to a degradation and will eventually fail at a certain point of time. Although the remaining useful life of an asset can be predicted thanks to IoT sensor and predictive models, still the maintenance quality and its associated costs are highly dependent on the skill set of a technician who carries out the task. Given that a skilled technician is not always available on site when the failure occurs, the question that we are trying to address is how could we effectively and efficiently provide access to the expert knowledge when it is needed. The conventional method is to use telephone and email to reach to a skilled technician. However, this approach leads to a long waiting time in communication and often misunderstanding, which result in loss in production time and inefficiency use of resources. At Cranfield University, we developed AR-based solution that offers a novel way of visualizing and exchanging information between a remote expert and a local technician. The intention of developed approach is to improve communication and therefore reduce errors and misunderstanding as well as time-consuming tasks. In the academic literature, we found 20 papers from 2010 to 2018 that address the application of AR for remote maintenance. This paper can be categorized into 4 main areas. The majority of the study was focused around process guidance, followed by training, remote assistant, and data collection. A further analysis into this literature, we identified at least 3 main areas that require further research. First is structured communication, refers to a way remote communication is regulated to reduce ambiguity. Second is automatic data collection, which refers to an automated mechanism for maintenance data gathering to improve maintenance communication during the collaboration task. The third is an expert system, which refers to a recommender system that can advise technician in troubleshooting a problem in unknown situation. This talk will focus on how AR-based remote maintenance, especially for diagnosis tasks, can be enhanced using structured communication. In order to address the question, the approach that we had taken was to develop AR-based remote communication framework, which was built on 2 main components. First, an innovative message structure, and then second is a rule-based authoring approach for automatic AR content creation. Looking at the left figure, we can see that conventional remote collaboration made use of telephone and email to deliver unstructured message and other related information. With this approach, it is difficult to ensure that a message is transparent or easily understood. because of a knowledge gap that might exist between a remote expert and a local technician. In contrast, our approach uses structured message and a rule-based authoring that decompose message into information elements and transform them into AR instructions that can enhance remote communication for diagnosis tasks. This is the example of message structure and AR visualization for both expert and technician view. At the bottom, you can see message elements of the message structure. The message structure was developed using the 5 Ws method. Using this message element, it allows us to address three main challenges. First is the ability to construct an effective message that can describe any procedures. And second is the ability to record and to replay a call based on the message logs. And third is the ability to automatically create AR instructions. The second element of the framework is the development of a rule-based authoring approach. In the left figure, we can see an AR instructions authored by a remote expert can be overlaid in the technician view in the real environment. Unlike the traditional approach, AR-based solution can provide two ways of awareness. First is the object awareness, which refers to the identification of the object being referred. Second is the procedure awareness, which refers to the procedure to be performed on the object being referred. And here comes the validation part. Our AR-based system implementation consists of three elements. First is a PC used by an expert to create AR instructions. Second is a cloud server that stores the information and provides data access to a database. Third is a technician HoloLens, which is a device used by a technician to visualize AR information in the real environment. HoloLens is equipped with a web camera that can be used to live stream what the technician is looking at to the remote expert. We carry out experimental validation to evaluate if the developed approach can actually enhance remote diagnosis tasks in terms of errors, completion time, and the complexity of the message. There were three different independent variables and two evaluations, which involves a total of 30 MSc students for performance evaluation and 8 industrial users for usability and feasibility evaluation. And here is some more detailed information of the experimental tasks that we asked our participants to carry out. There were 4 messages from simple to complex. Message A refers to a remote expert asking a participant to unscrew the screw of the front panel of the fuel hatch and open it. Message B refers to an expert asking a participant to visually inspect the left and the right side of the fuel hatch and take a photograph of every defect found. Message C refers to an expert asking a participant to repair any defect by placing a patch. Message D refers to an expert asking a participant to search and take a photograph of the previous reparation result and send it by email. Here are the results that we have obtained from our validation test. In terms of errors, we found that the number of testers who made mistakes during remote diagnosis tasks were similar across different experimental groups. This is also true for the total number of errors across experimental groups. which implies that the accuracy of remote diagnosis using augmented reality remain unaffected. In terms of time, we found that the reduction time for remote diagnosis was achieved using augmented reality solution. The average reduction time using AR was 56% in comparison to no AR solution. So it leads to more than half time efficiency, which entails to a better use of expert time. Furthermore, the reduction time was incremented as the complexity of the message increased. This implies that remote diagnosis using our AR solution can achieve more time saving as the complexity of the message increases. Finally, we also got the result of usability and feasibility evaluation from the testers and the industrial users' opinion. From the data collected, we found similar results between two user groups, which shows some evidence that our AR solution for remote diagnosis is indeed useful and applicable in real-life context. Therefore, based on our validation results, we can conclude that our AR-based approach using message structure and a rule-based authoring can be used to improve the efficiency of remote diagnosis in terms of time reductions. However, the total number of errors were similar between our AR-based approach and no AR in remote diagnosis. Further, we've also got the results that the experts feel were similar with the tester feels in terms of usability, utility, and feasibility to our AR solution. As part of the future work, we should address the efficiency of AR-based solution on the side of the remote expert. Finally, we should also address the potential use of structured communication for developing a recommender system. Thank you for attending this webinar. I'm happy to answer if there is any questions related to this talk.